detail on precision and accuracy.
Precision and accuracy are two terms that we can use to kind of talk about how good measurements are, and they mean different things. Precision is going to tell you how close measurements are to each other, whereas accuracy is going to tell you how close those measurements are to the real value. So, in order to better conceptualize this, think about a game of pin the tail on the donkey. Say you are confident where the donkey's butt is, and you have really good aim. Well, now you're able to place all of those tails directly on that donkey's bottom, and you get a precisely accurate measurement. But what if you're sure you know where the donkey's bottom is, but you have really good aim, but you were totally wrong about where that bottom was, and instead you actually are putting all your tails on the ear. Well, these tails are all going to be really close together, so your measurement is going to be precise, but it's not going to be accurate because you're far away from the true location. You can also have values that are around that true location, so they're all around the site where you want it. They're all on the donkey's bottom, but they're far apart from one another. So this would be accurate because if you're near the true value, and if you were to like average these all out, you would get a good estimation of that true value, but you're not precise because these values are really spread apart. So any one individual value would be less likely to be like a true value than if you were precise and accurate. And in the worst case scenario, you are not precise nor accurate. And so basically your values are, your tails are spread out and they're not around the right location. So even if you were to average them out, you would not get a good estimation of the true value. We can use different mathematical terms to describe the precision and the accuracy. So with standard deviation, this is going to tell us how spread out the values are. And so if you have what's called a normal distribution, you have something that looks like a bell curve, and basically the standard deviation is going to be kind of the middle of one standard deviation will be kind of like the middle of the curve. And then as you go further away in standard deviations, you're getting more towards those outliers. And so I'm not going to go into the statistical things of this, but basically there's a 68, 95, 99.7 rule where if your data is normally distributed, which not all data is, about 68% of the data are within one standard deviation of the mean, 95% are within two standard deviation, and 99.7 are within three standard deviation. So if you have a higher standard deviation, this is going to tell you that in order to encompass 68% of your data, you're going to have to go out further from the average data. And so the higher your standard deviation, the more spread out your data is. And the more spread out your data is, that's like having your tails be further apart. So the higher the standard deviation, the less precise the measurements. Now, this is if you have repeated measurements. But what if you have a single measurement? Well, if you have a single measurement, we still have a way that we can indicate precision, and this is through significant figures. So significant figures are basically telling you which values you're confident about and which ones are estimations. And the significant figures that you can get from a measurement is going to depend on your measuring device. So the closer together the lines of your device are, or the like gradations of your cylinder, or the ability of your scale, so whether you're using like an analytical balance or a kitchen scale or something like this, the number of digits that they can measure to is going to influence how precise your value can be. Because basically with the significant figures, you're saying all the figures except for the last one we're pretty sure about. So if we were to take a measurement again, we would still be likely to get that same first value, but it would be the last value that would differ. If your measurement device has bigger lines on it, well, then you're going to have less significant figures than if you had the smaller gradations, then you would have more significant figures. So for precision, if you have more significant figures, this is an indication of more precision, because basically, if you were to take repeated measurements, those repeated measurements are likely to be closer to one another than if you had to be estimating based on these bigger lines. And so although precision, we're talking about how close measurements are to each other in the case of multiple measurements, with a single measurement, it's kind of like theoretically, if we were to take another measurement, how close is it likely to be to the measurement I took before? So this is precision, and it's talking about how close the measured values are to one another, but it doesn't tell you about the accuracy. So for example, what if you forgot to tare or balance your scale? What if you forgot to take into account the weight of the weigh boat? Well, now all your values would be higher. The weights you're measuring would be higher than the true value, even if every time you measured, they were really close together. And even if you had a bunch of significant figures, if you went out to a bunch of digits, if you were really precise, you would still be inaccurate. And because because you weren't looking at the true value. Instead, if we want to talk about how close things are to the true value, we need the other term. We need accuracy. So accuracy is going to be how close you are to the real value. And it can be harder to know because, well, you're trying to measure the real value, right? One way you can tell is kind of like if you use different measurement tools and they all give you a similar answer. That's a good indication that you're going to be, that you're likely more accurate if you have these like kind of orthogonal or different ways of measuring something that are giving you the same value. You can also have like a theoretical value. And in these cases, when you know a real value, you can calculate how accurate you are with this thing called the percent error, which is going to tell you how close the value is to the real deal. And so basically the percent error is going to be the absolute value of experimental value minus theoretical value divided by theoretical value times 100. So basically it's going to tell you how like close your measurement is to the real value. But again, it can be hard to actually know that real value. And you can get deceived by having errors come into play with your measurements. And so this can be because of like your instrument error, or it can be because of like you doing something. So the like operator error. Basically, there's going to be little errors that happen every time that you take a measurement. In some cases, these errors are going to be random. And so one of the examples of random error that we talked about yesterday is parallax error. How if you look at the line of a liquid, say the meniscus, when you're measuring a liquid in a graduated cylinder, you need to look at eye level, because if you look at a different way, then the line is going to look like it's above the line. The liquid line is going to look like it's above the actual line or below the actual line because of this thing called parallax error, where basically the angle that you look from matters. And so if you were to look at from different angles each time, sometimes it would look a little higher, sometimes it would look a little lower. And this would be random errors that would basically balance each other out. But there's also systematic error. And so systematic error, an example would be if you were measuring every time you were measuring from the top of the meniscus instead of the bottom of the meniscus. And so you would be having systematic error because each time you would be measuring the value that was higher than what you should have been measuring. And so systematic error is going to be directional, while random error is going to be just like they're going to cancel out. With systematic error, they're kind of each time they're just kind of going to reinforce one another. And so you can end up with this biased directional error, where basically you can still be really precise but not accurate. And systematic error can also be due by problems with your instrument, like if your scale or your pipette is miscalibrated. And sometimes you can correct for it after the fact. But the systematic error, this is going to affect your accuracy. So to review, precision is how close measurements are to one another. And so it kind of describes the spread of the different measurements that we can talk about using a standard deviation. The higher the standard deviation, the larger the spread and the less precise the measurements. If we have a single measurement, we can indicate precision based on the number of significant figures. So significant figures are kind of the number of figures that we're confident in. And so if we have, say, finer lines on our ruler, we can be more confident about the smaller gradations. And if we were to take a measurement again, because you have to kind of guess between the closest two lines, if those lines are closer together, you can still have more precise values. You can get closer to one another if you have these smaller values that you're estimating between. So the finer your measuring device, the higher the precision you can get, the more likely that the next person, if they were to take a measurement, that would be close to the measurements that came before it. And so it was likely that if someone were to play pin the tail on the donkey again, they would be getting close to that tail that was before them. But that tail that was before them might not be in the right place. In order to talk about whether it's in the right place, we have to talk about accuracy, which is how close the measurements are to the actual value. So how close are the tails to the actual donkey bottom? And to talk about this can be harder to kind of know, because it can be hard to know the true value. But if you have different measurements, or like different techniques that you can use, or different measuring devices that are all kind of giving you the same value, that's a good idea that it's probably pretty accurate. In terms of the accuracy, we can talk about it if we know the real value or we know the theoretical value, we can calculate the percent error, which is going to tell you how close your value is to the real value. And this value might be influenced. Your measured value could be off because of things like random and systematic error. And the random error is typically going to cancel each other out. And so it wouldn't affect your accuracy, because your accuracy, when you're kind of like averaging all those together, they would cancel each other out. But with systematic error, you could get biased directional error, where you get this inaccuracy because all of your measurements are going to be off in the same direction. And so that is the basics of precision and accuracy. So remember, you can be precisely accurate, and you can be precise but not accurate. You can be accurate but not precise. And worst case scenario, you can be neither accurate nor precise. But all of these terms, but precision and accuracy are two different terms, and sometimes it can get confusing. So just remember that pin the tail on the donkey and happy measuring.